Hello everyone, this is Jim Corkins, and we are on 7.5, which is lenses. So if you haven't done the reading, this would be in Untitled Chapter 24, but also in the OpenStax reading as well. And I believe that would be Chapter 2 in OpenStax 3. So we are going to go ahead and talk about lenses, and these are mediums which are curved. So before we were studying how a single ray of light was going through a flat interface between air and water or air and glass. Well, now lenses are a more dense medium than air or a vacuum of space, but they are curved. Okay, and so when light rays refract upon a curved surface, you can get things where the light rays get focused to a point or diverted away from a point. Okay, and there are two main types of lenses that we're going to be studying. It's going to be, the first one is called a double convex lens. Convex meaning bent outside, right? And we're also going to be studying double concave lenses. So double convex lenses are also called converging lenses, and a double concave lens is also called a diverging lens. So just as we were talking with mirrors, how there were concave and convex mirrors, well, now there's going to be concave and convex lenses. Okay. There are also other types of lenses. Plano-convex lens, meaning plano means one side is flat and convex means the other side is convex, right? And then you have convex meniscus, where you have basically two kind of, you have a convex and then also concave. So that's convex meniscus. And there are those versions of the concave of the diverging lens down here. So converging lens is double convex or convex in nature, and diverging lens is concave or double concave lens. All right. Well, the thing about a double convex lens is that it causes light to focus to a point on the other side of the lens. So if you have parallel rays coming in and they hit a double convex lens, or what we're going to now call a converging lens, it makes the light rays converge onto a point on the other side of the lens. The antithesis of this is a diverging lens, which is a double concave lens. So when light rays are coming in from left to right, they refract through this lens, but the weird point is they don't focus onto a point on the other side of the lens. They actually, in a way, they kind of diverge away from the focal point on the same side of the lens as the incoming light rays. So this is a diverging lens. It makes the light rays diverge away from the focal point. This one is a converging lens. It makes the light rays converge onto a focal point. Okay, so that's why they're called converge and diverge. Okay. Well, we're gonna just concentrate on converging lenses for right now for the first part of this. Okay. So the rules for going through and drawing these rays are the same type of rules that you would do for the spherical mirrors that we did in 7.4. Okay, but here with this part here with converging lenses, what you have to do is instead of the light rays bouncing off and forming virtual images and real images, that's going to happen, but those terms are going to be reversed. Okay, so what we're going to be doing is we're going to be the procedure is the same. You're going to draw the optical axis, which is this mid-axis that cuts the lens in half. Okay, And then we're going to mark a line to draw the center of the lens. Okay. Actually, let me alter this here so that I can move this up and maybe even squeeze it down a squidge so I can move it up a little bit further, and I'll walk you through how I'm going to do this. And now I'm going to mark up the document. Oh, I should save this first. And I'm going to mark up the document. And so I'll draw this for you. And I'm going to draw it freehand because most likely all of you are doing the same. So you're going to, first thing you draw is the optical axis, which is just a center line. Okay? And with both converging and diverging lenses, you're going to draw the lens itself. Okay? But the most important, I didn't do a very good job of drawing this, I'm sorry. But the most important part is you're going to draw a bisector of that lens, and that's number 2 here. All right. Now you're going to draw the focal points. I'm going to, again, with a double convex lens, there's going to now be 2 center points, right? So if the right side of the lens right here is going to be a big circle. Whoops. And I don't want to go to that. Sorry about that. Is going to be a big circle. So that big circle is going to have a center, is going to have a radius here. But again, the radius the focal point occurs at half radius, right? Remember that? The focal point occurs at half the radius of the circle. Well, over here, now this side is going to be forming a circle. And that radius would probably be out here, but the focal point here, and I'm assuming these 2 curvatures are the same, is going to form a focal point right here. And if the curvatures are the same, the distance from here, from the center of the lens, the center line of the lens to the focal point should be the same as over here. I might move this over a squidge. Okay, so that should be about the same if they're, and we're going to only be working with lenses where both sides are the same curvature for now. Okay, so we listed off the focal points. Okay, now we're going to draw where we're going to place an object here outside that focal point. And I'm going to use an arrow, and that's how you traditionally do it. And this distance right here is DO, or as Knight puts it, S prime. S prime. That's the distance from where you place the object to the center of the lens is the object distance. The focal point distance is from where you place the dot for the focal point to the center of the lens. So that's really important. It's not that where the glass is, it's where the center of the lens is. Okay? Well, now I'm going to draw my arrows. Again, a parallel light ray is also called a parallax light ray. I'm going to draw that first. So I'm going to draw a parallel light ray, and it's going to come straight across. And then it's going to go down through the focal point. And it should be going in a straight line. That was kind of too curved for me. So that light ray is coming off the object through the center of the lens, and I'm drawing everything relative to the center line of the lens. And then it goes down through the focal point. It's best to use the straight edge, but I'm on a Wacom board, and I'm free drawing it, trying to draw much in the same way you would probably do in class. Okay? Well, now that you've got that drawn, you're going to draw another light ray that is going to go from the near focal point to the lens. Okay? So we're going to draw a light ray that goes down through the focal point, and then when it finally hits the lens, the center of the lens, and I'm using blue for that focal point ray, which is this one right here, goes down through the focal point from the top of the object down through the focal point, and then it goes parallel to the optical axis, Okay, and so you can see that they're converging right here, where the two light rays are interacting. But even though we don't have to draw this third one, I kind of like to just be sure, and I'm going to use green to draw this one. And this last one goes from the top of the object down through the center of the lens and then continues on in a straight line. And this would be like that curvature light ray that we did, where it was reflecting off the center of the mirror and then back out, or reflecting off the center of the mirror and then bouncing at an equal angle. But this one is going from here to there. It's going to continue on in this direction. So that's this third ray, okay? So you could see where all of these guys are interacting or intersecting. So this is where our image is going to appear, right? And so notice the image, I'm using baby blue for the image, I like that color. The baby blue, the image here is going to be upside down, right? And this is the image distance. The image distance is d sub I, or Knight uses S prime. That sounds like a transformer. It's not. I looked it up, so it's not. So where the image forms relative to the center of the lens is the image distance. That's d sub I or S prime. Okay? Well, images that form on the other side of the lens than the object, well, that is going to be called a real image now, right? So this is kind of opposite of what the mirror was saying. When an image formed on the same side of the mirror as the object, that was called real. But now we're dealing with lenses, and lenses refract, so the light ray needs to, a real image is now going to be on the other side of the lens. Okay, so that's how, and it's real because that's, notice these aren't dotted lines, and those dotted lines would be virtual lines. Solid lines are real lines. So that's the basics, and that's a procedure of how to draw this. Well, there's only really two types of drawings that you're going to have to do, just kind of like with mirrors. With mirrors, you had only really two types of drawings for what was it? It was a concave mirror, right? And one of the drawings was when the object was outside the focal point, and then the other one is where the object was in between the focal point and the center of the mirror. Well, in a similar way, this is kind of like that type of mirror, where it was a concave mirror. But this is a lens now, and it's a converging lens. The other one was a converging mirror. Anyways, this lens, there's one situation which we just drew where the object is outside the focal point. The next one that we're going to draw is when it's inside the focal point, in between the here. Okay. Well, let's take a look at those. Oh, by the way, this is the lens equation. It's actually the same equation. The magnification equation and the lens equation is the same for a mirror and a lens. And incidentally, magnification is equal to, well, magnification is also equal to comparing the height of the image to the height of the object. All right? And that's just the magnitude of it, right? So we don't care, like, you have to draw to determine that it's inverted if you're comparing the heights, right? But the lens equation and the magnification equation works for both lenses and mirrors. So, and this is called the thin lens equation. All right, let's take a look at the different drawings, okay? And I've just put those two equations above the two types of drawings for a converging lens. Here we go. You've got the one ray, and we just drew this. You have the object outside the focal point. So we draw the parallax ray. It goes down through the center of the lens, down through the focal point on the other side of the lens. Then we drew the focal point ray, or the F ray, and it goes down through the focal point and then straight across. And then finally we drew the center of the lens ray, which just went straight through the center of the lens and kept on going in a straight line. Okay, and where all of those converge is where this where the image is going to form. Now with this type of ray, when the object is really super far away, like let's say the object was way out here, really far away. Well, this image is actually going to form really small, okay? However, if the object is really close to the focal point, this image is actually going to be formed closer and then very large, okay? So we can't, drawing this, there's really not enough information to decide if the image is going to be enlarged or small or even the same size as the object, right? But what we for sure know is that the image will always be inverted and it will always be real. Real, again, meaning that it's on the other side of the lens as the object, okay? But whether or not the image is going to be enlarged, smaller, or the same size is going to depend on the object distance to the center of the lens. If the object is really close to the focal point, which means it's closer to the center of the lens, well, this is going to be enlarged. If the object is really, really far away, well, then the image is going to be really small. Okay? So let's go over the other drawing for when the object is in between the focal point and the center of the lens, right? So again, you follow the same procedure. You're going to draw a line, which is the parallel line, which is going to go through the center of the lens and then down through the focal point on the other side of the lens, right? The other drawing, which is going to be hard to draw because I didn't really complete the size of the lens. I'm just going to imagine it goes a little bit higher up here, and that would be lower down. I'm just going to, surgically add addition to that lens. Anyways, the focal point ray would actually come, I'm going to just draw the center of the lens here. Let's say the center of this lens goes all the way up and all the way down here. So it's going to go all the way up, all the way through down here. Okay, anyways. So if you're going to draw the focal point lens in this situation, it's got to go through, whatever line that you draw has to go through this focal point, right? Well, if you drew a light ray down through that focal point, it's not going to intersect with the lens. So in some way, whatever you draw has to converge with, has to hit the lens. So what we're going to do is draw a virtual image. And it's going to go up through this lens and then straight across right here. And that would be that focal point line, right? Well, tracing this back, we're going to give it a virtual line, and that line is now going to intersect with our parallax line that we drew, where then we drew a virtual line up there. Virtual meaning a dotted line. The final step in the drawing is you're going to draw a line that goes down through the center of the lens and keeps going. So all the M-ray line, I think we called it the center of mirror or center of lens line. Well, again, this is going to create another dotted line that is another virtual line, and all these virtual lines are going to intersect right here. So the image is going to form right here. So that's the image distance to the center of the lens. The object distance to the center of the lens is right there. And then you have the focal point, which is actually pretty close to this image. Well, when the object is in between the focal point and the center of the converging lens, you will always get an upright image. It will always be virtual, which means it's on the same side of the image, forms on the same side of the lens as the object, and it will always be enlarged. So these three things will always be true. Okay? And those are the two types of drawings that you need to know for ray tracing on converging lenses. And to do any equations, you'll use this. You'll use the thin lens equation and the magnification equation, which also, by the way, is if you want to just know the size, you could actually just measure the size of the image and divide it by the size of the object. And that's just the size. You have to draw it and then realize that if you do it this way with distances, it'll actually, and multiply it by a negative number, it'll actually give you a negative or a positive. Negative meaning if you end up working out the mathematics, it'll be upside down or right side up. Okay? Anyways, let's do a problem, shall we? Oh, let's do a couple conceptual things. Conceptual exercises. See if you can do it. Which ray tracing diagrams are drawn correctly and uniquely predict the location, size, and orientation of the image? Is A drawn correctly? Is B drawn correctly? Is C drawn correctly? Is D drawn correctly? So which, or is a combination of these drawn correctly? So which ones do you think? Go ahead and pause the video and go through the steps and procedures that we went through to draw. Well, turns out that none of them are wholly drawn correctly. The only one for sure that is absolutely incorrectly drawn is C. So let me go ahead and do this. I'm just going to get my tool, my comments tools out so I could actually draw on this. So what was lacking from A is a center of curvature line. So you need at least two lines to confirm that the the rays are converging to a point. And same thing with the object line. So it needed at least a center of curvature line. It also could have used, I like drawing all three, but when something has multiple sides, it starts to look like you're just drawing spiders. So here is the center, here's the focal point line, and here's another focal point line, right? So that just kind of looks really chaotic, but it confirms that A needed a couple extra lines. B could also use some extra lines too. You have this, you have the bottom part that draw the parallax ray line up through the top, and then also the center of curvature ray to the top. So you need two for each side of the object. C, none of the light rays emerge from the center and go up through and then down through the center. That's just showing the center is center. That's not going to show the tip of the image. So C cannot be correct. D, while it does have two light rays to show, and you do need a minimum of two, it would be better that you have a light ray, a parallax light ray to go down through the focal point, or come across parallel to the optical axis and down through the focal point on the other side. And then also another parallax ray up through the focal point to confirm the other side. So basically C is the only one that is for sure drawn incorrectly. A, B, and D are acceptable, but I would rather you draw more light rays. Let's try another problem. Okay? What would happen if you mark this up. You know an object right here, if this is the focal point, the object's out here, the image is going to form over here where all the light rays converge at this point, right? So here's where the image is going to form due to this light bulb. But have you ever wondered what would happen if you put a screen what kind of image would form where the light rays weren't overlapping on each other? So would a well-focused image form on both screens? On the first screen, not just the second screen. So what do you think? Yes or no? Would a well-focused image form on this screen? Or would an image form at all on that first screen? What do you think? So pause the video now and try to answer that and think about it. Well, if you notice, the light rays here are not converging onto a point like over here in the image. So we know a crisp image is going to form here. What happens is you will still get an image here on the other side, but it's going to be out of focus. So it's going to be a blurry image. Blurry image. But you're still going to get an image there, but it's kind of like when you're trying to take a picture of someone and they're out of focus and you have to kind of move the lens back and forth to try to get the image more in focus, right? So it'll still be an image form, but it'll just be a blurry image, right? And what you need to do, you need to actually add another lens here to make it converge even more, to move the focal point closer so that you move the image closer along with the focal point. So you'd have to add another lens or thicken this lens to do that. So pretty cool. You still get an image, but it's just a blurry image, right? Let's try another conceptual problem. Suppose you have a candle, and the light from the candle is going to go through the lens, and it's going to form a nice crisp image right over here. What do you think is going to happen to that image if you cover up half the lens? Would half the image show? Well, basically, would the image still show on that screen over here, or would half the image show? Or since you're covering up half the lens, the light rays may flip the image upright instead of being upside down. It'll now be upright, or will also be flipped and also half the image. So what do you think is going to happen if you cover up half the lens so that half the light rays can't get through? What do you think is going to happen? Pause the video now and answer that question. Well, what happens is this. Some of the light rays are not going to get through. So that parallax light ray that comes from the top of the object is going to end up hitting and stopping right there. It's not going to be able to go down through the lens because this is an opaque object, right? Well, the parallax light ray from the bottom is going to go through the lens and form up top. And also from the bottom of the lens, the center of curvature one is going to go up through and form to the top. So, but you're not going to, what the weird part is the top of this light ray is going to be able to go through and form at the bottom, and then the focal point light ray from the top of the object is going to form at the bottom. So you're still going to get an image, and it's going to be focused. It'll be focused, but it'll just be dim. So it won't be as bright or intense as the image as this image where the lens was not blocked. So it'll still be a focused image, it'll just be dim. Okay? Pretty neat. Well, now let's do some ray tracing for the other type. Let's continue on with the other part of the when you have the object in between the focal point and the lens here. So we've kind of done this before, but let's just revisit it. And this is how Knight presents it. Notice he's using S as the image object distance to the center of the lens. And then, so he does the same thing. He draws a parallax ray, it goes down through the focal point, and then a virtual ray comes up. He's going to then draw a center of curvature ray down through the center of the lens. And then that virtual line is going to come up. And then he's going to draw a focal point lens. It's going to go straight across, and then that parallel part is going to now come over. And where they all form is going to be the virtual image. So the virtual image distance to the center of the lens is at S prime, right? By the way, the focal points are the same on both sides. Well, now that we've reviewed double convex lenses or converging lenses, let's do a problem. To see a flower better, a naturalist holds a 6 centimeter focal length magnification lens. So that means it's going to be a lens that is 6 centimeter focal lens. But he's going to put flowers 4 centimeters away from the center of the lens. And he's asking, what is the magnification? Well, what this means is the focal point is a greater distance away from the center of the lens than the object. Well, that is this situation right here. So what we know is when we draw this, the focal point is here, and I'm going to actually put 6 centimeters right here, and this is 4 centimeters. Well, that image that is going to get formed is going to be a virtual image, it's going to be upright, and it's going to be magnified. So we should expect the magnification to work out to be a positive number, okay? So it's going to be a positive number, so S prime, the image distance, so what we would do is we would work it out where you have 1 over the image distance plus 1 over the object distance is equal to the focal point, right? Well, we need to find out the image distance here. So I'm going to subtract both sides. Subtract the object distance from both sides. So this is the focal point minus the object distance. And so S prime is going to be equal to 1 over the focal point minus 1 over the object distance to the -1, right? And so when he worked that out, 1 over 1 over F, so let me do this, S prime, so that's the image distance, 1 over, I thought the focal point is 6 centimeters, minus 1 over 4 centimeters is going to give us S prime, which this is going to work out to be 12 centimeters, or actually negative 12 centimeters. So, because 1 over 6 is smaller than 1 over 4, and that's going to work out to be negative 12 centimeters. Well, now, to find the magnification, now the magnification is equal to the negative of the image distance over the object's distance. So that's going to be a negative of negative 12, so it's going to be positive 12 divided by 4, and that's going to work out to be 3 times the size. This is 3 times the object size. So it's going to be very enlarged. It's going to also be virtual, and it's going to be upright. Virtual, again, means the image is on the same side of the lens as the object. Okay, this is a cool problem. I think he has it drawn right here. So yeah, basically that's the drawing that we were just using. Pretty neat. Well, let's move on. Let's move on to the other type of lens. So with converging lenses, there were 2 types of drawings that we had to draw. One where the object was outside the focal point, one where the object was inside the focal point. Well, with diverging lenses, even though you're following the same procedure that you were doing with mirrors and also the converging lens, the rays here only produce one type of image with a diverging lens. It doesn't matter where the object is, outside the focal point or inside the focal point, you're going to get the same type of image. Okay? So again, a diverging lens, light rays coming from left to right hit the lens and then they refract through. But rather than refract through, they're going to be diverging away from the focal point on the other side of the lens and basically creating a virtual image on the same side of the lens as the object. Okay? So again, you're going to be following the same steps that you did before. You're going to trace the optical axis. You're going to then draw. I got to mark up the document here. So you're going to write the optical axis. Let me move this over here so I can make a mini drawing. Make a mini drawing. Mini-me drawing. Okay. So you're going to trace the optical axis. You're going to draw the lens. I'm going to draw the lens right here. That's the center of the lens. And I'm going to give it... Actually, I'm going to use... a black line for the center of the lens, and I'm actually going to draw the lens in baby blue. So the lens is going to be here, and it's going to be a double concave lens. I'm not doing a very good job at doodling, and I apologize. Double concave lens. And there you go. I'm going to emphasize that center of the lens line, just like we did before. So this is the center of the lens, or that's supposed to be the center of that horribly drawn lens. Anyways, you're also supposed to indicate the focal point. Again, the focal point occurs at half the radius, so if this is a circle, the radius would be way out here, so I'm assuming the focal point will be right here. And there will be a focal point, if this is the same kind of thing, that'll be over here, the same distance, if it's the same curvature, right? Well, now I'm going to draw the object. And again, you're going to draw the object and label it, and label its distance, DO. Here's the focal point. The object distance to the here is going to be DO. The focal point image here is going to be F. Okay? Well, here we go. Let's do some ray tracing. So the first thing that you're going to do is you're going to draw a parallel light ray, right? So light ray is going to come straight across here. But when it hits this point, the cool thing is it's going to bend away from the focal point over here. Let me redraw that. And so this is that focal point, is that parallax ray. Okay. Let's draw another light ray. And we're going to do a center of curvature light ray. And it's going to go down through the center and keep going in a straight line. Okay. And so it looks like they're coming together right here. Well, just to make sure, let's draw that focal point light ray. Again, the object is going to create a light ray down through that focal point, and then it's going to go straight across. Actually, I drew that incorrectly. Whoops, I can't believe I did that. We're actually going to draw it so it goes down through the focal point on the other side. Okay? It's going to go down through the focal point over here and act like it's going to continue on. Then it's going to go in a straight line. Well, tracking that to right here. Cool. Well, our image, we've drawn all three of our lines. Our image is going to be formed, is going to be right here. And it's going to be, it looks like it's going to be upright. So this is the image distance, or also S prime. The object distance is just S. So the image distance, which is right here, this image looks like it's going to be upright, it's going to be virtual, and it's going to be smaller. Okay? Pretty cool. Well, here is a better drawing than mine, and this is really the only thing that's going to happen. Because even if we've drawn it, and let me try to get a piece of paper, even if the object is inside the focal point here, the image is going to actually form right over here. So let me draw that for you in a second here. I'll try drawing that for you on the next page, but let me just summarize what the drawing that we just did. So again, what you're supposed to do is draw the optical axis, which is right here. You're also supposed to draw the center of the lens, okay, which I drew right here for you. Then you're going to label the object, which is DO or S, depending on which book you're using. Okay, then you label the focal points, which occur, again, the focal points occur at the half radius of curvature, right? Again, this is the curvature of this side. So that radius is going to be way out here, so that's a half focal point. The focal point over here on this side, if this is the circle that's forming, it's going to be a big radius, so this is about the half distance, right? So after you've drawn the focal points and you've labeled the object distance and the object distance, you're going to then draw a parallax ray. It's going to go straight across, it's going to bend away, it's going to diverge from the focal point over here on the right side of the lens. But really what's happening is virtually converging on the same point over here. So in a way, anyways, I don't want to complicate it, but so you draw these virtual lines. Any dotted lines are virtual lines. Now you're going to draw a center of the lens line, right? It's just going to go straight through, and now you can see them crossing. And then finally, you're going to draw another light ray. It's going to come straight across. So you're drawing it as if it's going to converge on the other side, but then it just goes straight across. And then you backtrack that here. So they all overlap. And so the image that forms here is upright, reduced, and virtual. So it's going to be smaller in size, it's going to be upright, and it's virtual. Virtual, again, meaning it's on the same side as the object. Let's try doing another drawing where the object is inside the focal point here. Okay? I hope this turns out well. So I'm going to draw the center axis line, optical axis line. Okay? I'm going to draw the center of this lens. Okay. Now I'm going to actually draw the lens. And try to draw it very carefully. Okay, so I've got that. That looks pretty good, right? Not too bad. Okay, well now I'm going to label the focal points, and I'm just making a best guess as to the focal point. Half radius. Okay, good so far. Now I'm going to draw the object. I'm going to draw the object right here. and I'm going to label it. Okay, DO. All right, I'm going to try to use some different colors now. You use red for the parallax light ray. That red light ray is going to come straight in, hit the center of the lens, and it's going to diverge away from the focal point. But really, so this is going to come straight across, diverge, and it's going to diverge away from that focal point right there. Cool. Cool, cool, cool. Let's draw a center of curvature light ray, and let's use blue for that. So the center of curvature light ray, we're going to be using blue, and it's going to go down through the focal point from the top of the image and continue moving in a straight line forever and ever. Okay, that's good, and it looks like they're coming together right here. Well, let's just be sure. Let's use green. How did that change to green? Oh boy, here we go. I'm going to draw this again. Draw the center of curvature line straight through. Center of curvature is blue. Parallax ray is red. And now I'm going to draw the focal point one. Okay, and I'm going to use green for that. And I'm going to draw it so it's going to actually draw, and almost I'm going to try to draw it so that it's intersecting with this guy over here. But where it hits the ray, it's going to actually be backdrawn here. So it's going to come through, and I'm going to draw it like it's going to hit the, like it's going to try to focus over here on the other side of the lens. But where it hits the lens, the center of the lens, it's going to backtrack here with a dotted parallel line to the optical axis, and they seem to all converge right there. Okay, and so here is where the image will form. It'll be a nice little pink guy, and that is the image distance. And so notice that this, no matter where you place the object, whether it's outside the focal point or inside the focal point, that the image is always going to be in between the object and the center of the lens. With diverging lenses or double concave lenses, no matter where you put the image, it's going to no matter where you put the object, whether outside the focal point or inside the focal point, the image is always going to form in between the object and the center of the lens. And it will always be upright, smaller than the reduced in size from the object, and virtual. Okay? So here is basically the summary of what we just did, right? So we have a double convex lens, okay, and with a double convex lens or a converging lens, if the object is outside the focal point, it's going to produce a real and inverted image. Real meaning it's on the other side. Now, how far away from that center of lens that object is, it's going to determine whether it's going to be reduced to the same size or enlarged. Okay. However, when the object is inside the focal point of a double convex lens or a converging lens, you will get a virtual image that is upright and much more enlarged than the object size. Okay. Finally, with a double concave lens or a diverging lens, the object will, no matter where you place the object, the image form will always be virtual, upright, and reduced. Okay? I hope you enjoyed this. Please move on to geometric object like eyes. So how do you apply this stuff? It's almost like the application. So please move on to that in 7.6, I believe. Let me see, is it 6? Are we going to be all the way in 6? Yeah, 7.6. All right, bye.